Hey everyone, Recipes for Thrive and Survive, June 19th, 2015. We're going to start a new subject today. This will be part 3 in the Why Lie series. But we're going to finish off first with the last video that I did. I want to clear up some things there. You know, it is unbelievable to me that people cannot imagine in their mind that even with the curvature of the earth, that something is desperately wrong with what we've been told. But since they can't think that way, I'm going to explain a few things here, and then we'll move on to the next subject. What we have here, thanks to Joe Schmo, now even more famous, for sending me this link. And to me, guys, this was a miracle. I went to the site yesterday. I was looking around, and it explains a bunch of different things. And it ended up being like 3 or 4 in the morning. I was like, man, I got to go to bed. So I closed my lid and on my computer, and it turns off the light on it. And then in the morning, I opened it up. Now, I always open it up by grabbing the left side of my screen and pushing it up. And I do have a computer where the screen is active. So if I push a link with my finger on the screen, it is a touch screen. It will load a link. And here's what was amazing. I went back and looked at this because this opened up as soon as I opened up my lid to my computer. There was no link on the left side. So I don't know how this opened up from this site, but this gave me the answer I was looking for as I was thinking last night when I went to sleep. You see, you're never going to have, unless you happen to be down near the equator regions, you're never going to have the sun directly overhead as far as north, south, east, and west, okay? But there's a thing called the meridian line, and no matter where you are, once a day the sun crosses the meridian line over you. And what that means is, let's just say you're the observer down here, and the meridian line is this round line coming up here. And as the sun rises in the east and comes around, when it gets to this meridian line, the shadows on the ground will not be east or west any. There'll be no east or west shadow under things. It'll be the north-south shadow. There'll be a shadow to the south because you're not far enough south, the sun's south of you. But this is the high noon thing right here. So, you know, Miami, I was able to get it to like 89.86 degrees overhead. You never do get 90 because you're too far above the Tropic of Cancer. Cancer. So anyway, this is the meridian. And what my thing is, what I'm trying to point out is at the meridian time, which is 12 noon, give or take 15 or 20 minutes. You know, it really depends on where you are in the time zone. And I'm using the center part of the time zone in both cases here. When it is the spring or fall equinox, you're going to have equal day and night. So you will have 6 hours where the sun is getting up to this position, and then you'll be at the meridian, which is an imaginary line over your head when you're facing the celestial North Pole. You won't have any, if you hold something or look at a car or whatever, it won't have a shadow except to the south. There will be no east-west shadow, so you can't tell from that if you are facing east or west. You can tell if you notice where the south part of the shadow is. Face that shadow. Left is to your east, and right is to your west, and to your back is north. But then it takes another 6 hours for it to go all the way down and set on the other side of the horizon. All right, and the time is equal. So when you're 3 hour time zones away, the sun is down here if you head west. If you head east, it's down here, halfway between the horizon and up here. Since the Earth supposedly turns equally throughout the day, we don't have any acceleration or deceleration periods. This all works with the math. And I've got the math solved, and let's go there now. I think you're going to be quite surprised. Okay, I came to the site here, which gives you all kind of different kind of triangles and things like that. I kept trying to do an obtuse scaling triangle, but it just got too heavy into the math, and there was one thing I was always missing. It was either an angle or the height or the base or something I was missing, just one shy of being able to solve it. So there's another way from other examples I saw in here that reminded me actually from school how to do this stuff. Anyway, what I did was I took the base here, which is A, okay, which is 7,913 miles. I'll explain that in a minute. That's actually the diameter of the Earth at the equator, 7,913 miles, all right? And the hypotenuse, which is B here, all right, this is 5,996 miles. And you're going to see how I got that. That is going to be from the top of the, you'll see it, okay, top of the globe all the way down 45 degrees. Now this is 6 time zones away. This would be sunset while this is noon. Okay, I'm doubling everything. What I showed yesterday was only a 3-hour time zone difference, which would be here on the triangle. But I wanted to make it easier and prove that we don't have a sun that's 93 million miles away. No way, no how. Okay, here's the formula for it. H equals the square root of b squared minus a squared over 4. Theta equals tangent -1, 2h over a, and then s equals 1/2 ah. All right, so you math people know that. The height then is 4,505 miles. That's what I was looking at. I don't care what the, what else does it give you? The area. I don't care what the area is. So anyway, what I'm looking for is the height, which is this number right here, the height. How high is it? All right, so now I have all 3 sides of the triangle. Let's go to the next thing. Now, I don't know if anybody out there who knows math can do this. And by the way, the person that gave me a bunch of math, I tried to respond to you, but then I lost it. Google lost it for me again. I'll find it and get back to you. I appreciate what you wrote, but I have some things to write back about what you wrote. In any case, imagine this is the Earth, and we were talking about the sun being at noon. 3 time zones over would be 45 degrees over on the Earth. Okay, and this is all from what science tells us. There are 12 time zones, and let me show you that because people are going to get lost here. Okay, each one of the spokes in the wheel here represents 3 hours of time on the Earth. Okay, 12 noon, 3 p.m., 6 p.m., 9 p.m., midnight, 3 a.m., 6 a.m., 9 a.m., and then back to noon again. Do you see that? So each line is 3 hours difference. And that's what we were showing. That can you see that at 6, this would be at noon, 3 p.m., 6 p.m. A person standing on this part of the Earth would be seeing sunset on the spring equinox, assuming the sun is right over them. Okay, they're at the spring equinox. This is at the Tropic of Cancer. All right. At the same time, noon, right here would be the sun directly overhead. All right. Now I computed from this. What we were talking about in the last video was 3 time zones over. The sun would be 45 degrees in the sky, all right? But it works better at 90 degrees, all right? So that's what I did, because 90 degrees, because everybody was like, well, you're not taking the curvature of the Earth into effect. So when we get here, you're going to see I used all that. This is almost like if you flip this on the side, this is what they tell us the Earth is. It's an oblate spheroid. And we're going to cover that in another video. But in any case, I have computed that the angle from the sun overhead to a person standing 3 time zones away, which is roughly 3,113 miles. All right, I extended this red line beyond the circle just so you can see where I'm talking about. But right here in the middle of this circle, that from this blue line here on the top is 3,113 degrees. Now, the curvature of the Earth in that distance is 992 miles. And if you want to know how that's obtained, you take the miles times the miles, all right, times 8. All right, that gives you how many inches. Divided by 12, that will give you how many feet. Divided by 5,280, that will give you how many miles. So I have added 992 miles curvature to the figure that we're going to be looking at. So even that's involved here. Although I think the distance that Google Earth will say is between this point and this point already covers it at 3,113 miles. I added it anyway, and I added a lot of other stuff just to make it work. Okay, so now again, I have the cheap version of the NASA software, so my circle isn't exactly right. It looks more like a little bit of an egg. But anyway, with this kind of triangle, you can figure out everything from that math site that I just showed you. All right. Now, with that being said, let's come over here. Actually, this whole video is going to be this. I don't want this to be that long. What I did was the diameter of the Earth is 7,913 miles at the circumference of the at the center of the Earth equator, and that bulges out some, not much, from the rest. It's really very close. But I'm using all the larger figures just so there's no question. All right, I know up here it's not as wide. But I'm giving everything to you here. 7,113 miles is the whole distance across the diameter of the Earth here. The radius would be half of that, all right? In any case, so then we can start making some computations, knowing that B is 5,996 miles. Now, how did I get that figure? From the North Pole to the equator, using the Earth's curvature, you get 5,996 miles. Okay, that's how much you would travel along the Earth to get there. So we know what the distance is. If we take the North Pole down to here, to the equator, actually on the straight line, it would be 5,996. All right, good enough? All right, now, how far is the sun above the Earth? Forget this little blue indentation for a second. I'll show you why that's here in a second. You take that same triangle and go through here, and then all you have to do is label it like this triangle is. This is the exact same triangle, it's just turned over this way. If I had the advanced software, I could rotate it 45 degrees and just put it out here and you would have seen. Okay, this here, right here, all right, this is called an isosceles triangle, all right? All three angles are the same. They're all three 45-degree angles. That's what's so nice about this. And here we have an isosceles triangle, the exact same size, but now in the red, 45 degrees, 45 degrees, 45 degrees, okay? 345 degrees. 1, 2, 3. All right, now, here's what I did. What I wanted to do was I wanted to see how far would the sun be from the observer here, even though it is 3 hours beyond noon. Now, you have to take the mirror image of this, all right? But it just made more sense for me to do it this way. But take the mirror image of this, or act like you're on the other side of the Earth looking down at this, and this will make sense. In any case, you take this right here, all right? This becomes H, which was here. All right. These B's, okay, now if you take this line in here, that's H, 4,505 miles. That's what I computed. But how do we get there? B, line B is 5,996 miles. The same as this B over here. It's the same side. It's just rotated to the right. 5,996 miles. This B here is 5,996 miles. So how long is this red line down to this triangle inside the Earth? That is 4,505 miles. Okay, 4,505 miles. And I've added 992 miles curvature to the figure, and I've taken the fact that from here, I'm not even on the surface of the Earth. I'm taking it from slightly inside the Earth. The sun is 4,505 miles from the observer. If he was inside the Earth here, if he's on the surface, you have to subtract whatever this is. Folks, the people that say it's about 3,100 miles, that's going to be right. That's absolutely going to be correct. The observer up here would see this, in his case, this would be 3 hours early. It's not to noon yet. It rotates up this way. So at 9 a.m., the distance to him is 5,996 miles. All right, now this is all assuming that it's a globe, and that's how the math works. Okay, you cannot have a 93 million mile away sun and have the speed of the Earth as it turns. You cannot have time zones that are 3 hours apart. All right, like this. Every one of these spokes is 3 hours apart. If it's 93 million miles away, okay, again, you would be less than 1 degree angle down here on the hypotenuse. So you would never see the sun's rays at angles. So everybody that said, well, you're not showing it on a global Earth, not only am I showing it, but I'm giving you everything. And I mean, I'm throwing in everything but the kitchen sink and coming up with 4,505 miles away from the observer. And this point right here is probably 900 miles inside the Earth. It's interesting. It's close to 992 miles difference here. But if you were standing right here, it's probably 3,000 miles to the sun. So you can prove it, guys. You can prove it by what science tells you. And the math, I mean, this did the math for me. All right. It used this formula and came up with the numbers. If you don't understand this, I'm not pulling a trick on you or anything like that. Talk to somebody who understands math. Please. They will tell you I'm not pulling any tricks on you. The math is correct. The sun absolutely, no way, is 93 million miles away. And now we've taken the curvature of the Earth in, and I don't know what else to say. I mean, oh, this blue line here, that would be A divided by 2. This A here, I just decided to break it in half and look at both triangles separately. It all comes out the same. 4,505 miles, and that's me adding everything and taking at the equator when it should be a little bit smaller figure up here. Like I said, I threw every possible advantage into people who think that the Earth is much further, I mean the sun is much farther away from the Earth. So I hope that proves it now that we've looked at it on a globe. And guys, why can't people think like this? I mean, do they really think the globe would have made a 92,900,997 mile difference? It's unbelievable. This is trigonometry proving how far the sun is. And we know that because we know how far 3 hours away is on the globe. And we also know from what I showed you before with the sun declination and things like that, the meridian line, that how it works. Okay, and there's another calculator on the site that shows exactly that. And when it is the spring equinox and at 12 noon, give or take 20 minutes, you have that meridian crossed above your head, that artificial line. And then 6 hours later, you have sunset. 6 hours before it, you had sunrise. And it's quite even throughout the day. There's no acceleration or deceleration, as we know. So the math works. What doesn't work is 93 million miles. If you have an issue with this, well, this is what NASA's telling you. Take it to them. Thanks.